Hello and welcome everybody to lecture video 7.1. In this video we will look at 2D motion estimation in camera images and this will then form the basis for visual odometry that we will introduce in the next video. So just as a quick recap, remember again how a camera works. We have 3D objects in space and those objects are imaged by a camera, by a projective camera, and we model this using the pinhole camera model in week 3. The idea is that we have a point in 3D and this point gets projected onto an image plane this relationship between the 3D point and the 2D point on the image plane is given by the camera intrinsics matrix K. And then at this point on the image plane we have a light sensitive cell that measures the intensity, and this intensity is then being read out, and this gives us our digital image. So from the mathematical side, this means that we can define an image now as a function that maps from this image plane to intensity values. Of course, if we have a color camera, then this image function would map to a three-dimensional vector where the components then correspond to the red, green and blue intensity. Realistically, of course, this image function is only defined on a rectangle because it's only defined there where you actually have your sensor. Then this dimension is defined by the width and the height of your image. When we are talking about digital images, then of course this image function is only sampled at discrete locations. So if we need, for example, to evaluate this, or if you want to evaluate this image function at a location somewhere in between, then we will have to interpolate between these sampled values. If we need to take this into account when we need to compute derivatives and so on, that this is done in the proper way. But this also means that digital images, of course, can be represented as a matrix, where you, for example, would enumerate from left to right and from top to bottom as we know it. So back now to our original problem of estimating the 2D motion of an image. The problem there is that we assume that we are given two camera images, probably two consecutive images, F0 and F1. And we assume that the camera has moved a little bit in between, and so our goal now is to estimate the camera motion u in between these two images. And for the moment we assume that the camera only moves in the XY plane, so there is no rotation, it's a pure motion in the image plane. And we will then later see how this extends to 3D. But this means that at the moment we can represent this camera motion by a two-dimensional vector u that just describes the translation along x and y axis. Good. And now the general idea is as follows. We define an error metric that describes how well the two images match given a particular motion vector. And then the second step is that we need to find the optimal motion vector that yields the lowest error of this error function e. And and there are different choices here for the error metric. The most common one is called the sum of squared differences, abbreviated as SSD. And there the idea is just that we directly look at the differences in intensities. So when we're summing over all pixels, but for every pixel we take the difference between the intensity from the first image, F0, and then from the intensity in the second image, F1, at this pixel plus this motion vector u. And this difference is then squared and summed up, and this is why it's called the sum of squared differences. Just as a shorthand, because we will need this later, we call this difference term here the residual error. And by introducing this symbol, the equation for SSD becomes much shorter because it's just the sum over the squared residual errors. Good. Now, of course, one problem with SSD is that especially when we're talking about digital images, that our images have only a finite size. And this might mean that as soon as we run out of the image, or if we move one of the images with respect to the other one, then the overlap actually gets smaller and smaller. And because this happens, the error by itself gets smaller, because we can't compute any error of pixels that do not overlap. So this means that the standard SSD has a bias towards smaller overlaps. So it prefers actually to shift apart both images to have zero overlap and thus zero error. And this means that the standard SSD is not enough generally, but a very simple solution is then just to divide this SSD error by the overlap area so that this is normalized out. And this is then called the root mean square error, where we just take this error divided by the number of pixels and take the square root. A different way for computing this error term is to use cross-correlation instead. And then instead of minimizing the differences, we seek for maximizing the product of both images. The intuition behind that is that we are trying to align both images. And so when they are aligned well, we would assume that they correlate very well. And this means then that the product between the two images is actually maximally. So you can think of this as if you have somewhere bright spots in your image, say a white line, then when this white line coincides with the white line from the second image, then these two correlating pixels will yield a very large value for in this cost term and then indicate a good correspondence. One problem with normal cross-correlation is that the absolute value of this error function depends strongly on the content of your image. So if you have a white or very bright images, then this cross-correlation will yield a very large number. And if you're looking at a very dark scene, then automatically this term will be compared relatively low. And therefore it's desirable to normalize that somehow. And then one straightforward extension is the so-called normalized cross-correlation, where you subtract the mean value of your images from both input images, and you divide by the variance of both, or the standard deviation of both images. And this automatically gives you then a score between -1 and 1, and then you have it's more easy to interpret how good your match actually is between the two. And one huge advantage in contrast to the SSD is that the normalized cross-correlation is much less sensitive to illumination changes. And illumination changes, of course, can happen quite frequently if your brightness in the room changes or the scene you're looking at changes. Then the camera might decide to increase the gain or reduce or increase the shutter time. And then SSD will not be able to match the images very well. Good. So back to our algorithm. So we've now defined an error metric E that we can use to evaluate how good a particular match is. And now we need to find the motion vector that actually minimizes this error function. And there are different ways of doing this. One option, of course, is to do a full search in the neighborhood. So if you can make assumptions on how far your image probably has shifted, then you can do a brute force search for the minimum. This is actually sometimes done because this guarantees you then that you're actually finding the right minimum. But in most cases, this is not necessary, and people just run a gradient descent-like approach or a Gauss-Newton method. And there are even ways then to make sure that even if you have larger motions, to still find the right minimum using a hierarchical decomposition. Good. So the most common type actually is to run a minimization, gradient-based minimization method called Gauss-Newton. This was introduced by Lucas and Kanade in '81. And this is probably the most famous and the most popular method for tracking motion in 2D images. And it's moreover, it's extremely efficient. So the general idea behind Gauss-Newton minimization is that we linearize the residuals or the error function with respect to the camera motion that we have. This then yields us a quadratic error function that we can derive and from which we can set the derivative to 0, and then we can and then this gives us normal equations that we can solve with just by inverting this matrix. So now from a mathematical side, we start out again with this SSD error function. Remember that we just take the difference between the two images. We shift the second image by this vector u, take the difference, then compute the square of that, and then sum over all pixels x. And this term we now want to linearize in u, so we add a small increment to our current estimate of u. So we evaluate it at u plus delta u, and then we make an approximation with respect to this delta u. So this Taylor expansion then looks as follows. The insight here is that this delta u only appears in this term f1. f0 is not shifted, only f1 is shifted by this delta u. And so we can approximate this nonlinear function by evaluating f1 at xi plus u at the original point, plus the Jacobian evaluated at xy plus u times our increment delta u. And and this Jacobian is nothing else but the derivative or the gradient of the image evaluated at this particular location xi plus u. And the gradient is just defined as the partial derivative of this image f1 with respect to x and the partial derivative of this image with respect to y. Now, of course, we want to minimize this error function or the approximated error function. As you know, at the minimum of a function, its derivative has to be 0. So for finding the minimum, we can actually now derive this error function and set its derivative then to 0. And this is not very complicated, so if you want to try this out by yourself, just go ahead. And then if you summarize the terms accordingly, then you end up with this very simple linear form here shown in the middle. We obtain this 2a times delta u plus 2b has to be 0. And then these individual terms are composed by these Jacobians. As you remember from this last slide, this Jacobian is nothing else than the image gradient, actually. So these this matrix A and the vector B can directly be computed from the image gradients, where this fx here stands for the second image derived with respect to x. Fy stands for the partial derivative of the second image with respect to y. And this ft here is actually just the difference between the two images. Some people also call that the temporal derivative if you're looking at consecutive images. Good. But now that we have such a simple linear system that we need to solve, we can directly invert this matrix A or solve it directly using the Gauss elimination method. The cool thing now is that all of the computations that we have to do to find the minimum are extremely efficient because we just need to evaluate the image gradients and sum over them to build this matrix A and B. And then we have to solve a 2x2 linear equation, and that virtually costs no time. Good. So one strong assumption, of course, that we have here is that we assume that the image gradient is actually meaningful, and this, of course, only is meaningful, or this Taylor approximation is only valid as long as we're not moving away too far from our linearization point. And then, of course, this depends a little bit of our image, how well this linear approximation actually holds. But it's clear that the further we actually move away, or the further our image patch is shifted, the more difficult it will be with such a method to find the right minimum. And now one very easy and actually often used method for enlarging this convergence radius is to perform a so-called hierarchical motion estimation, where you're not directly estimating the motion on the image itself, but you scale down, or you downsample your image in a pyramid, where every layer of the pyramid halves the resolution. Instead of having 640 by 480, you would have at the next layer a resolution of 320 by 240, and then 160 by, 120, and so on. And at these higher levels, even a larger motion on the original image actually appears just as a motion of 1 or 2 pixels. And then our linearization holds again, and this means that we can run this Taylor approximation. And now the idea of this hierarchical motion estimation is that we estimate the motion first on a very coarse level, maybe 3 or 4 levels higher than our original image. And then when we determine the motion there, we use that as the initialization for our for the Taylor approximation for the next final level. And in this way, you can improve the convergence a lot. Good. Another interesting thing to note here is that we can also evaluate the quality of our estimate by looking at this matrix A. This looks as follows. Imagine that our observed image is, of course, noisy. So it is a noisy observation of our true image or of our true pixel xi. And every pixel adds then a small error term that is, again, normally distributed according to a certain variance. And then it can be shown that this noise in the image actually results in an uncertainty of the motion estimate that has a covariance of this sigma squared times a to the minus 1. So by evaluating this matrix A or the covariance of our motion estimate is inversely related to this matrix A times the variance of our image noise, sigma square. Good. This actually is, this method that you've just seen is actually widely used. Everybody of you, whenever you touch optical mouse, actually runs this algorithm directly on a chip. It can, of course, be implemented easily on a CPU, but it can also be implemented in hardware, and then it becomes very energy efficient and so on. So a typical mouse sensor actually runs at very high image rates. This has the advantage that even if you seem to move the mouse very fast, the motion between 2 consecutive images is, of course, extremely small, and then this Taylor approximation holds very well. Gamer mice, for example, run at even higher frame rates, and then you get an even better resolution or motion estimate. And actually a computer mouse just has a very low resolution camera. You don't need too much here. Some even go down to 16 by 16. Some have a little bit more, but they are very cheap to produce. And as I said, everything is already built into the chip. Then you directly get the X and Y velocity that you can send over PS2 or USB to your computer. Good. This was now a method to align whole images, but sometimes you're just interested in the motion of individual patches within an image. Then, of course, the question is which patches or which points in the image can we actually track, or which patches should we actually track. And it's clear that some patches are much easier to track than others. Obviously, if you have a lot of texture, it's easier to track than if you don't have texture at all. And so the question is, how can we automatically recognize good patches that are easy to track? And just to visualize the different possibilities that we have, if you are looking at a corner point or a point that has a strong texture in both directions, in X and Y direction, then our patch actually is very easy to track because it is constrained in all directions. However, if we happen to look at a patch that is that's looking at an edge in the image, then it will be constrained very well in this in y direction, but actually the patch can move arbitrarily in x direction just because there is no information in the image that tells us where it actually exactly was. And then the other extreme is that we're looking at a patch within a unicolor region, and then of course it's not possible at all to track it because all its surroundings look exactly the same. And just as an example how this looks for real, this is now an image taken from a real image taken by a camera. And we again have here these different types of things. For example, if you look at this green, the first patch at the roof of the house, then we're getting this problem of an edge. So the energy here depicted on the right is actually we actually see a valley, so it's not really clear which minimum we should pick if we track this patch. Then the next patch is the red one, where we don't have any texture. You can also see here in the surface plot of the energy function, it doesn't have a very clear minimum. Of course, there always is, by definition, a minimum, but it's not very easy to find and not very unique. Good, and then actually a good patch is here shown in blue on the bottom right, and this is a situation where we have lots of texture and where our energy function shows a clear minimum. And these are actually the patches that we are interested in because those patches are easier to track. And now, as we said before, we can recognize the quality of our motion estimate from this matrix A, which is also called the Hessian. And so if this matrix A is large, then our covariance of our estimate is small, which means that we are very well localized. And this big and small can also be read off from the eigenvalues of this matrix. So if we compute the eigenvalues lambda 1 and lambda 2, then if these two eigenvalues are very large, then we are actually looking at a corner. If only one of them, if the first one is large, the second one is small, then we're looking at an edge. Then we are constrained in one direction, but not constrained in the other direction. And when both of them actually are small, then that means that we have a very high uncertainty in both directions. So this is certainly not a good choice then for an interest point or a key point. Good. So there have been various corner detectors proposed. The oldest or most famous one is the Harris detector. It actually does not need eigenvalues because those were complicated to compute at that time. So there is a simple approximation where you just have to compute the determinant of this matrix A and the trace of this matrix A. Essentially, it is still looking at the product of both eigenvalues and compares that to the squared sum. Later, when computers got faster, the Shi-Tomasi or Kanade-Lucas corner detector was proposed that just says that if the minimum of the two eigenvalues is actually larger than a certain constant, then we consider this to be a suitable corner. Good. There are other detectors as well, like the Fürstner detector that can localize a corner even with subpixel accuracy. This certainly helps if you need highly accurate estimates of points in your image or patches in your image. There are also fast corners that became popular, very popular over the past years, where you apply a machine learning technique to actually, reduce the number of pixels that you have to read out. And this means that the fast corner detector is extremely fast and even much faster than this Harris detector. Another popular one is the so-called difference of Gaussians that is used in the SIFT feature descriptor, which is even scale invariant. The Harris detector, for example, recognizes a corner only at a particular scale. If you would zoom into a corner, then this corner might given the right zoom, appear as a more or less straight line, and then the Harris detector wouldn't recognize this anymore. And the idea of difference of Gaussians is that you again build this image pyramid and that you search for corners at all levels of this pyramid, and this means that you're invariant, or at least somewhat invariant, to a scale change. Good. And now we finally come to the Canade Lucas Tomasi tracker, one of the most popular and famous trackers in the world for 2D motion estimation. The algorithm is as follows. We first find the corners in the image, typically these Tomasi corners, and we do that in the first frame and then initialize our trackers. So every corner gets a track, and then we track this corner from frame to frame using this Taylor approximation from before, and this is Gauss-Newton method. And then we, if it happens that this matrix A, or that the eigenvalues, if they're not localized anymore, or if the discrepancy gets too large, then we delete the track. If we lost too many tracks, then we can initialize additional tracks when necessary. This is a costly operation because for that you have to scan the whole image for corners, so you don't want to do that too often. Only if your number of tracks gets too low, and then you repeatedly run the steps 2 to 4. The good news here is that the KLT tracker is extremely efficient, so it runs in real time on CPU. There are many open source implementations of it in OpenCV, but there is also a tutorial for MATLAB, for example, and essentially for all languages that you can think of. The KLT tracker only tracks these sparse points in the image, but it is also possible with other methods to compute a dense optical flow, where you essentially for every pixel in the image find this motion vector u. And this is typically a bit more complicated, and for that you need more processing power, which at least at the moment requires a GPU. Good. So now to finally demo how this looks like for real. This is now just a camera video that somebody took and then ran a KLT implementation on it. And as you can see, these red points here initially are the Tomasi corners. You can see small numbers. If you look carefully, those are the track numbers that are being tracked. And then when the camera moves, the algorithm tries to track them using this approach that we've shown. And of course, it can happen that tracks get lost simply because either they fall out of the image or the matching doesn't work for some reason. We have an overexposure or a blur in the image, and then the tracks might get deleted. Good. So to summarize the video of today, we've looked at 2D motion estimation. We've introduced different cost functions that are typically used. We've shown that this is the technique used actually in computer mice. And computer mice, as we said, look at aligning a whole image to the previous image. If you're only interested in tracking small patches, then it makes sense to pick good patches. For that, we looked at corner detectors, and then we applied that in the KLT tracker to track different regions in the image. And this now will be used, this technique we will then use in the next video to estimate visual odometry for a quadrotor that has a downwards looking camera.